talking about.
Thanks, Ravi. And so today I want to give a broad overview of these tensor decomposition techniques. We've worked on for almost like more than 2 years now for unsupervised learning of various latent variable models. So these earlier works were in collaboration with Shyam, who's in the audience, Daniel and Rong. And Shyam will be giving a talk on Thursday, so he'll go into some of the more details I won't be covering here. And the more recent a line of work on like overcomplete latent variable models with Rong and my student Majid, I'll kind of give some overview of the results of those as well. So, unsupervised learning is a challenging problem. If I have these latent variable models and I have only unlabeled samples without labels telling me which, what are the hidden components from which it was drawn from, then this is more challenging than the supervised setting. Right? And this occurs in a variety of different settings, as Ravi covered yesterday, the topic modeling setting where I have documents where I just have these word occurrences but not labels of what topics occurred in the documents. That's what I'd like to discover. Hidden Markov models, community detection problems in social networks. All these are examples or unsupervised learning problems. And in general, for almost all of these models, if I want to ask for the maximum likelihood estimate, right, that's a NP-hard problem. So although that would be statistically efficient, computationally, that's a hard problem. So we'd like to come up with both computationally efficient techniques as well as those that require a small amount of number of samples for learning, ideally some polynomial, computational, and sample complexities. Right? On the other hand, like the methods that are widely employed in practice, such as expectation maximization or variational relaxations of the likelihood function, they have no consistency guarantees. So they're not guaranteed to converge to the global optimum. They are not guaranteed to recover the parameters of the underlying model consistently.
You don't mean it in that generality, do you? I mean, there are certainly theorems of consistency of both.
In some very highly limited cases, right? Especially for EM, you need like separation conditions that tend to be not satisfied in many cases. So the question is, and I'll come to the the details. At least in most cases, these do not have consistency guarantees. And can we come up with a framework, an alternative framework with consistency guarantees and with efficient computation and sample complexity bounds? And we'll see how tensor methods can provide an answer to that. So indeed, if I want to think about latent variable models, I broadly think of them as like kind of these simple models where you have these clusters. So think of the hidden variable as just like selecting one cluster versus the other. Right? It's a categorical variable. Like these are like Gaussian mixtures or topic models where there's just one topic in each document. So this is the simple model, but ideally we'd like to be able to learn these more advanced probabilistic models where these hidden variables can have much more general distributions. So you can think of the LDA model or the latent Dirichlet allocation where in each document now you have multiple topics appearing. Right, so in these cases, there's no longer like a notion of separability of the clusters because all these different documents have overlapping topics. So you can similarly think in a social network setting, instead of thinking as people belonging to a single community, they now have memberships across different communities, right? These communities overlap. So in those cases, especially clustering techniques would be challenging to solve, right? Because there's no notion of separability. So again, can tensor methods resolve such challenging probabilistic models and learn the parameters consistently? So these are some questions we'd like to answer. So, for tensors, what I'd like to think of this as a moment-based method. Right? So indeed, if I have my samples, I can easily compute the empirical moments. The first order moment is the mean, then I have the variance, then I have skewness, and so on. And this is a classical approach, right? But mostly in the univariate setting. There's the classical Proni's method, which says like if I have moments up to some order, I can recover the parameters of the model. right? But with the univariate setting, I need high order moments because I need enough equations to solve for the parameters. On the other hand, in the multivariate setting, even low order moments can have sufficiently enough information, and that's what makes it interesting in many of these settings. So for instance, with just pairwise moments, I have a matrix, right? And now with the third order moment, I have a tensor. And the question is, for various latent variable models, how informative are these moments, and when can I recover the parameters given only this moment information? Right? So that's the first question of identifiability, having moments up to some order. And then the second question is computational tractability. So what are the algorithms to find the parameters given these moments? So the question is, for different latent variable models, how can we resolve this? That's the question I'd like to address. And as a notational viewpoint, I'll be using this cross product notation. Right? So if it's for vector x, if I take x cross product x, this is a second order tensor. And if I want, an entry I1, I2 entry, that's nothing but looking at the cross moment between those corresponding indices of x. And with this notation at hand, we can extend it to tensors as well. So if I have now a third order tensor, what this tensor encodes are the cross moments between any triplet of variables. And the question is, for different latent variable models, what are the forms of these tensors, and how can I learn the parameters given this information? Right? So, I'm sure all of you here are aware of the classical spectral methods which typically operate on matrices. Right? So here the idea is you do PCA on usually the data matrix or the covariance matrix of your data, find these top eigenvectors, and then do operations by projecting your data onto these top eigenvectors. Right? So it's been shown the spectral clustering would have much better noise tolerance than doing clustering in the ambient dimensional space. But these techniques, at least the classical ones, would mostly work only if these models are these single membership models. So it's the idea that it's a Gaussian mixture, or there is a document with only single topics. If I have mixed memberships, there's no longer a notion of separation, as I mentioned. And indeed, for these algorithms to work, you also need the separation to be large enough compared for these clustering to work. Right? And if the clustering doesn't work, then I don't know how to learn the parameters. And so the question is, are there ways to get around these requirements by going to higher order moments? Right? And indeed, there are more sophisticated clustering techniques, as Ravi talked about yesterday, which can go beyond these single membership models. But the question is, if that is not the case, can we look at higher order moments and use that for efficient learning? So the motivation for going now from matrices to beyond to tensors is many different points. Right? So the question is, can we learn mixture models without any separation requirements? So, as the separation gets worse, maybe I'll need more samples to have efficient learning, but there's no failure. Can I ensure that if I have higher order moments? So the second question, as I said, is unified frameworks, right? So thinking about these models with single membership versus multiple membership models, can I have the same algorithm to learn both these scenarios? And of course, the question then is, how do I think about a spectral method on now tensors instead of matrices? Right? So these are the questions that arise if we now want to go beyond matrices to tensors. And indeed, for matrices, the spectral decomposition is now nothing but writing the matrix as sum of rank 1 components. Right? And we can think of a similar analog now for tensors, where I want to express the tensor as, again, sum of rank 1 components. And the notion of rank 1 for a tensor is analogous to the case in matrices, because if it's a rank 1 tensor, the corresponding index in a tensor, say I1, I2, I3 entry in the tensor is nothing but given by the corresponding product of these individual vectors. Right? I mean, this would be the same in the case of the matrix as well, just that its W would be missing. So you can think of this now as an analog of rank 1 for tensors. And the question is, so suppose I had think of this M3 as the moments given from certain distribution, and suppose, I'm promised that it has this form. This form is known as the CP decomposition or the canonical polyadic decomposition. The question is, when does such a form give me the parameters of the model, and then how do I compute this form efficiently? Right? So in matrices, I mean, the theory is very well established. We know that it's identifiable up to orthogonal components and up to having an eigengap between these different components. Right? With the tensor, the story is very different. It turns out that you don't need orthogonality for identifiability. So in fact, you can identify components even when there are more number of them than the dimensionality of these vectors. So you can have the tensor rank being even more than the dimension, which is not the case with the matrices. On the other hand, computing these decomposition for general tensors is a NP-hard problem. Right? So we don't want to deal with general tensors. The question is, for many interesting latent variable models, do we have special forms of tensors which are computationally tractable? So can we find the decomposition efficiently? And that's what we'd like to analyze for those special class of tensors. Right? So I'll just very briefly give this tensor decomposition method. Santosh covered the method in the previous talk, and Shyam will also give more details. But just the idea is, suppose, say, this tensor was orthogonal, then it turns out that a tensor power iteration method will solve the problem and return the components. So you can think of an analogous Rayleigh quotient maximization problem, same as in matrices, and it turns out that the only stable fixed points are the components themselves in the orthogonal case. And the notion of a tensor power method is a quadratic operator in contrast to the matrix case when it is a linear operator. And if you do these iterations, what we showed was you will and this was also known previously, that you will converge to the correct components. And in general, of course, we will not have an orthogonal tensor in many of these latent variable models, but it turns out, as Santosh mentioned, you can whiten the tensor and make it into an orthogonal one. Suppose, for instance, I had like pairwise moments that also involve the same components AI. Then I can, whiten that second order moment M2, and essentially, which means like I'm like finding the linear transformation that makes it into an orthonormal basis. And such a transformation is invertible if I assume that these AIs have full column rank. Right? So under non-degeneracy assumption, I can find this whitening transformation, which is invertible. So I can convert this tensor, which is not orthogonal, to an orthogonal tensor. And that is obtained by doing essentially a multilinear transformation along each of the modes of the tensor. And think of this as like implicitly it'll carry out this operation, right? So it'll like kind of convert these vectors AI into an orthonormal system. And typically, as we're doing this, it'll also reduce the dimension because usually, like the number of hidden components is much smaller than the dimensionality in the space in the ambient ambient dimensional space. So this whitening will convert it to an orthogonal tensor and also, result in dimensionality reduction. So just putting this together, Shyam will give more details. But the idea of this is, suppose I had moments of this form, where the second order moments had like kind of essentially bilinear forms in these vectors AI, and the third order moments are like trilinear forms, again using the same vectors AI. Suppose I was promised that this is the form of the moments, then I can find these components correctly, right? This is, if I only had the matrix version, I would not be able to find the components uniquely because I'm not promising you orthogonality, right? These AIs are not orthogonal to one another. But now with the tensor, just assuming this very mild assumption that these AIs are just linearly independent, we can guarantee that you will correctly recover these components. So that's the power of tensors compared to matrices, right? So with matrix, you could not obtain the information easily. But with now tensors, we can extract these components. And the way to do this is some very simple operations. For the whitening step, you essentially need to do SVD of these pairwise moments. And these multilinear transformation, you can do this implicitly. Then after the power iterations, you again kind of need to do linear transformation to bring it back to the ambient dimension, because you solve for the orthogonal tensor decomposition in this reduced dimension space. So this is the overall method. It's very simple. In fact, we'll see later on some experiments that I have that this is easily parallelizable, this is very fast, and this even on like challenging real data sets, it'll give very accurate results compared to especially likelihood methods, which are slow and has convergence issues with large-scale data. So any questions so far? Yes.
Can you go over what W is again?
So W was the whitening matrix. So this is the transformation that converts my set of vectors to an orthonormal basis.
You know.
And you can find this by whitening this pairwise moments. And that is done to SVD. Right, only a rank K SVD is what you need. And since, like usually in practice, we'll see that this rank K SVD usually turns out to be the bottleneck step because my ambient dimension D is much larger than the rank K. And you can do like randomized methods to make this scalable and fast. So we don't need to do the exact SVD. And the other steps are much faster than the first one. Okay, so that's the broad overview of the method. In our earlier papers, we had like, polynomial sample complexity results. In the case where I don't have the exact moment, but perturbations of it, what is the level of perturbation we can handle, and what are the guarantees we can provide. So this is now a guaranteed method because we have consistency results and polynomial sample complexity. And of course, very efficient computation as well. So now the question is, I presented this under the assumption that I have these second order and third order forms. Right? The question is, for various latent variable models, how can I obtain these forms? Right? Do just the raw moments give me these forms? What kind of manipulations do I need to get to this form? And that's why I think of this as a unified framework, because for various different models, like some initial pre-processing will bring it to this form. Right? And then we have the same algorithm to solve for all these different latent variable models. So now let's see how the forms look like for different models. As Ravi yesterday introduced, the popular unsupervised learning problem is one of topic modeling. Right? So here I have a corpus of documents, and each document has multiple topics, and given a topic, the word is drawn according to some conditional distribution. Right? So this is now like kind of a mixture of topics for each document. And in the LDA model, these the mixing weights for different topics are drawn from a Dirichlet distribution. And so the question is, how do we learn such models, and what are the form of the moments for these models? So, geometric picture. Ravi also had a picture yesterday. So I can think of like now these proportions of topics in different documents as various different points on this simplex, right? The simplex with k vertices, where k is the number of topics. So, it's like if it was just a single topic, I would only be getting vertices, right? So this is like the basic mixture model. But in general, I would have, if it's like each document has multiple topics, I would have like these points all over the simplex. And in the case of LDA, it's a Dirichlet distribution for drawing topics, for drawing points on the simplex. And the idea is once I draw points on the simplex, say for instance in the simple single topic case, I'll draw words according to this conditional distribution. So here I'm like representing the words as a one-hot encoding, where say if the first word was apple, I would represent it as vertex in some simplex where the number of vertices is the number of possible words. Right? And the second word is something else. But the key point is this is a multi-view model where all these different word draws are conditionally independent once I fix what the draw of topics are. And that's what makes this learnable, because I have a large number of words that are conditionally independent given this hidden variable. And in the case, I mean, since I represented these words as these vectors, basis vectors, right, I can write the generation process as this linear model. So this is now nothing but, you can think of this as probability vector of words given this mixture of topics is nothing but just the combination of columns of this matrix A. Right? So columns of this matrix A are the topic vectors. Right? So these are the conditional distribution of words given the topics. Right? So there are k columns if there are k topics. And the question is, what are the form of moments for this model? Right? So let me first do just the single topic setting. So in this simple setting, each document just has one topic. So this is now nothing but the naive based model where the conditional distribution is the same for all these components, for all these words. Right? It's an exchangeable model. It's a very simple model. And in this case, what are the moments looking like? Right? So indeed, like the, what I know is that the conditional expectation of any word given the H is encoding which topic was drawn for that document is nothing but selecting that particular column of this matrix A. Right? And W is now nothing but the mixing weights, right? What are the probabilities of different topics for appearing? And so it turns out that the pairwise co-occurrence matrix is exactly the form that we saw before, right? So how is this? This is obtained by conditional independence, right? So this is now nothing but the probability of like the first word and the second word, right? Or since they are all exchangeable, this is now nothing but the probability of co-occurrence of all possible words in the same document, right? So what is this probability? This is now nothing but first with probability Wi, I draw topic I, and once I draw topic I know that the topic vector is just AI, right? And both these words should share the same topic vector because there's only one topic in this document. Is this form clear? And because of the conditional independence, it's nothing but AI cross product AI, right? So it's only of this form. Right, so this is just a simple consequence of conditional independence. And the third order moment will also just turns out to be similar by the same explanation. Right? With probability Wi, I draw topic I, and if it is topic I in this document, then the topic vectors are AIs. Right? So it's AI tensor 3. And now I'm averaging over documents, so that's why it's this sum over all these topics. So for the single topic model, the form that I showed was solvable is directly obtained by looking at the co-occurrence of pairs of words and co-occurrence of triplets of words. Right, so then the question is, what about these more complicated models I was describing where there are more than one topics in each document? And that's the result we had in NIPS a couple of years ago, where we showed that indeed if I directly look at the co-occurrence of the words, that won't have this CP form. But if I made some minor adjustments under the assumption that this topic draws are Dirichlet distribution, we can obtain the same form as we had for the single topic setting. And this alpha naught is nothing but like the overall concentration parameter of the Dirichlet distribution. I mean, intuitively, if this is larger, that means the topics are more mixed. You tend to have more topics in your documents. And this is something, in fact, we'd like to be able to tune in practice because we'd like to control how mixed I want my results to be. And that's what we can do this by having this knob here of controlling the moments. Right? And after that, it's the same algorithm for all these possible models. Okay? So it turns out that for various other models as well, as Santosh showed, like for the ICA model, again, you can reduce it to the CP form. Same like for hidden Markov models, you can again have this form. It's just like an asymmetric version of this, but that can also be resolved. I mean, there's some very similar, small modifications to handle that scenario as well. Right, so for all these settings, we have the same unified algorithm. So a more challenging setting that I'd like to describe is now one of learning hidden communities from graph data. Right? So you can think of like various nodes in the network, and the question is, when do they form social ties? Right? So the idea is they are belonging to some unknown communities, and that's what drives the social connections. So for instance, there are some unknown amount of membership into various different communities, right? Somebody likes to work with computers, play tennis, or dance, and so on. And there are also some unknown probabilities of forming a connection, given that when they meet, they draw with some probability that particular community. So for instance, in this example, you can think like for these pair of nodes, I first randomly draw the community according to this probability vector here. And based on the draws, there is some unknown probability that they will form a link. Right? So this is my generative model. So again, like the conditional independence will help us resolve the moments of this model. We'll assume that all these edges are conditionally independent given these unknown draws of community memberships for all the nodes. Right? So that's the intuition. There are these hidden factors that are driving these connections. I'd like to find them from my data. Right? And the special case of this model is the classical stochastic block model. In that case, every node just belongs to one community. Right? This is the extension. Now nodes can belong to multiple communities. And we'll assume that there are Dirichlet draws for how these communities are drawn. And this model was proposed by Edo Eraldi and others, but they use like kind of these expensive variational approaches to try to learn these models. So what we'll see is tensor methods can give very efficient ways to learn these models. So the idea is, in the graph setting, the problem becomes much more interesting because I have different ways to write down moments. Right? Like all different kinds of subgraph counts, I can think of them as possible moments that I can compute once I have the graph. And the question is, which moment is efficient for learning and kind of falls into our framework where I showed like the CP form of tensors. So it turns out that if I compute like kind of these star with 3 leaf, these kind of structures, moments based on these kind of subgraphs, we can have the same framework we had earlier for topic models and ICA models. So the idea of how exactly I do this is first I'm going to partition my graph randomly into 4 sets, right, non-overlapping sets. And what I'm going to do is look at every triplet of nodes in these sets here and count the number of common neighbors in across the cut. And we're kind of doing these nodes into different groups to kind of remove some dependency that you will shortly see in the next slide. But is the form of the moment clear?
In what sense subgraph counts are graph moments?
I mean, like we have a random graph, right? So the question is what kind of, so the subgraph would like give like some aggregate low order statistics of my data. And the different subgraphs will give me like different combinatorial structures.
But they don't have properties of
But I mean, you can again like kind of have concentration bounds, and the question of like like which subgraph counts characterize the graph, right? That's an open problem. I mean, the subgraph polytope is a notoriously hard, object to work with. But we are asking at least for this special, this specific random distribution of graphs, what kind of subgraph moments are enough to learn the parameters for consistent learning. So we are looking at only the very special case of this graph moment problem.
Completely get it. So, of course, any subgraph count is some low degree polynomial.
Exactly. But
I guess the point is that some of these polynomials you're able to factorize? Or?
Yeah, this particular polynomial that I described will give a CP form of the tensor.
Which is the particular polynomial?
So this one.
Okay.
So.
But more generally, which graph?
So in general, that's what it's not clear, right? If I had these different moments, how do I efficiently use all the information for learning probably more complicated models than this Dirichlet distributed community models? That's an open question, and I think a very hard question to answer. But in this particular case, if I constructed moments where I looked at triplets of nodes and asked how many common neighbors they have across the cut, then I have a third order tensor. And we'll see under these conditional independence relationships, this will give an efficient CP form. Right? And the main idea of why this is true is think of like any common neighbor here for set of edges which go into these sets, right? And all these set of edges are conditionally independent once I tell you what are the community memberships for this node X. And that's why you can think of this now as a multi-view model, where the set of edges are conditionally independent given this hidden variable, which is the membership of this node to various communities. Right, so as a graphical model, this is exactly the representation. If I think of pi x as my hidden variable, which encodes the distribution of, which encodes the membership of node x into these different communities. Right, this is the Dirichlet draw. And once I condition on that, I draw the set of edges that go from node x to the set A, and similarly here to set B and set C and so on. And because this has now a very similar form to like topic model, right? Here the interpretation is like, this is like these set of communities are like kind of topics for this particular document. And these are like kind of this first word, second word, and so on. So you can kind of see this analog between topic models and community models, although the data is very different, the model at the outset looks very different.
So just to clarify Santosh's question somewhat, if you had a triangle,
yeah,
then you wouldn't have conditional independence, is that right?
Yes, exactly.
So you cannot
exactly. Yeah, so to exploit this CP form and this particular algorithm, we need like a structure like this. We need this conditional independence and we need this multi-view model. And this is one way to generate it. The question is with other algorithms, probably the other moments would also be helpful, right? As some of the earlier works that you and Santosh have looked at, looking at triangles and the single case of like planted clique, what information that has, right? That's a different question. Right, so it turns out that for these community models, by constructing moments in this way, where I look at these common friends among triplets of nodes, I can find an efficient algorithm to recover the parameters of this model. So this appeared in Colts last year. I won't go into details, but like kind of the common parameter setting for this is usually in the stochastic block model there is this probability P for connectivity within a community and probability Q for connectivity across different communities. Right? I mean we can handle the more general non-homogeneous case, but let's just take the simple case here for to exhibit the results. And this alpha naught is like the concentration level of Dirichlet, which roughly encodes like on average what is the sparsity level of these community memberships, right? For each node, how many communities does it belong to? And I mean, the more this number is, the more mixed the communities are. So what we show is that the number of samples, which is the number of nodes in the network, needs to be like scaling as k square, where k is the number of communities. And in this simple case, I've just assumed all communities have the same size. And there's also dependence on this Dirichlet parameter as like a low-order polynomial. So the special case of this model, as I said, is when this concentration parameter is 0. Right? That's the stochastic block model where each node just belongs to one community. So in this case, what we have is like a tight scaling of like the sparsity levels needed. So intuitively, if I have a sparser graph, it's harder to learn the communities. And what we show, this bound is conjectured to be like the computational bound for learning communities. I mean, tight results are known when the number of communities is 2, but for general case, it's still an open problem of characterizing these bounds. And so these are the scaling requirements we have for the stochastic block model, but also now for the more general mixed membership models. And so we can. It turns out that we can. I meant like recovery is possible, but what does it mean by recovery, right? So what we show is, I think we show like for every community there's like an L1 norm error of like computing the memberships of all the nodes into that community. Right, so we can give like tight guarantees for that. I mean, good guarantees for that. And perhaps like an interesting interpretation of the result is in terms of like recovering significant memberships for every node in the network. The idea is, if a node has, say, this node J has significant weight in community I, I'd like to be able to infer that that is a 1, right? So I threshold like these large weights as 1. And the weights that are small enough, I'd like to threshold them as 0. And what we show is under these sample and the sparsity requirements that I described in the previous slide, we'll get this to be correct, right? We get the 0 error support recovery guarantees for learning these mixed membership communities. Any questions here? So I mean, such guarantees are also possible for other models, but I thought I'll describe it for the community setting since there are various other methods that solve the problem for the stochastic block model setting. And what we show is we recover the guarantees for stochastic block model, but now also handle this mixed membership setting where now nodes can belong to multiple communities.
Is there real data where communities make sense?
Yes, so that's what I want to describe in the next few minutes that I have. So we, so these algorithms are very efficient for parallelization. That I, argue is a significant strength of this method compared to like likelihood-based approaches, right? They are much harder to parallelize. That's because these consist of very simple linear, algebraic, and multilinear operations. So in fact, like this rank k SVD, where k is the number of hidden components, you can do this through randomized methods in a distributed fashion. And this tensor power iteration, in fact, if you want to speed is the requirement and it's very large scale, you can do this as a stochastic update. Right? I mean, the batch update would be slower, but with stochastic, you don't even need to form the tensor. You can implicitly find the gradients and do the updates online. And then this unwhitening is just linear transformation to bring it back to the ambient dimensional space. So it turns out that in the community setting, n is the number of nodes, k is the number of communities, s is the sparsity of each node, meaning the number of edges that each node has. Usually all these real-world graphs are extremely sparse. It turns out that these quantities parallelizable depending on how many cores I have. And in this case, I've assumed that the number of communities is small enough to be done on a single machine. So this rank KSVD of a k by k matrix can be done on a single machine. So that's why this parameter is k cubed, but if k is large enough, you could further distribute this operation as well. So the idea is these operations are extremely parallelizable for very large-scale data sets. And these are ideal for like GPU implementation because these just consist of simple BLAS operations, right? So just to show, like if we ran this stochastic tensor power iteration on a GPU, I mean there's like a kind of a more sophisticated programming where there's a device level interface where you can control the communication between CPU and GPU. What we show is we get a very good scaling as we increase the number of communities compared to like other settings. So of course there's like this MATLAB tensor toolbox by Kolda that's definitely not competitive with a GPU implementation as we expect. Right, but like the message is, I mean, we have the GPU code available online, and these methods are very suited for running on GPUs. And these results that I show are for the CPU implementation on a single workstation and varying, kind of sizes of the network. So we have like the community setting, like the Facebook with friendship network, or DBLP, which is the a co-authorship network. But we can also handle like these recommender system setting where users rate different products, right? In this case, like users write reviews on Yelp about various businesses. So in this case, we only look at the edges and not the text, right? So we are not looking at what the text, the review text they wrote, but only the fact that which user rated which business. And the question is, just looking at this graph information, can we recover attributes of these underlying nodes? So in all these cases, we had the ground truth, right? In DBLP, we have the information of what journals or conferences people submitted to. You can think of these as communities of the nodes. For Yelp, for businesses, we have like whether the business is a bar, is it a restaurant, all these attributes. So the question is, how well do we recover these attributes given just this graph data? And we compared it against the variational code given by Dave Bly's group. And so indeed, I mean, these methods are much faster than variational updates. That's not so surprising. But what's surprising is, like, in terms of these error measures, we have very comparable or even better recovery rates compared to the variational approaches. And you can see, like, on just a single workstation, we could handle up to 1 million nodes and do a very efficient learning of communities of all the nodes in that network. And that's the strength of these methods. And just to show kind of some qualitative results on Yelp data, we could recover, if we looked at the top communities, right, that were recovered, indeed, as we expect, like restaurants are recovered efficiently, but also like some of the smaller communities such as hobby shops, mass media, they have efficient recovery because the intuition is you have like these dedicated set of users who go and specifically review these hobby shops, right? So, and what the measure we are using are like kind of common users who are reviewing a set of businesses. So this like encoding such information in the tensor, even if you argue that these conditional independence relationships may not apply, is kind of informative of these communities. So these methods can be very powerful in recovering small communities in practice. So that's something we observe. And the other strength of this method is since we have a mixed membership model where we recover multiple attributes for businesses, we can now, kind of say that a business is a restaurant, it's a bar, what location it is, and so on. Right? So compared to a pure community model where you classify a node just to one community, now we can recover a large number of attributes for each node. And that's another strength of these mixed membership models compared to just the pure community models. So, I think I'm almost out of time, maybe another few minutes. I want to cover the most recent results. Some of this is ongoing work with Rong and Majid of how to go beyond what I described so far. Right? Algorithmically, we looked at the case where I have this non-degeneracy assumption, meaning the different components of the tensor are linearly independent. In this case, I can orthogonalize it and I can recover the components. But the overcomplete regime is the case when I have the rank of the tensor being larger than the dimension. Right? So this is the NP-hard regime where the hard problems lie. The question is, at least for some special scenarios, can we give guaranteed recovery? And the intuition is I can no longer have orthogonality because I have more components than the dimension. And this is where we'll make the assumption that they are instead now incoherent. Right? I mean, this notion of incoherence is popular in many settings. I mean, you can think of I want to find an incoherent representation of my data. I'd like to learn features that are incoherent with one another for classification tasks and so on. And our question was, when can we learn such decompositions? And what we show is that guaranteed recovery is possible when the tensor rank is kind of polynomially larger than the dimension. So for third order, it's like d to the 1.5. Up to that point, you can recover answers that are close to the true components. And for this, we need a bit more than incoherence. We need spectral norm bounds on this matrix A as well as bounds on the tensors and so on. But all these are intuitively, they're satisfied by, if you think of these components as being random, and even if the scaling is slightly worse, we'll just have degradation in what rank we can go up to. So kind of our result characterizes, depending on the various incoherence and the spectral norm bounds, what kind of recovery we can obtain. Right? And this works in the overcomplete case. And we also have a recent result which addresses the problem of sample complexity. Right? So the question is, now I have this empirical tensor. Can I come up with tight concentration bounds for this empirical tensor? And we don't want to do a naive matrix Bernstein bound by matricizing the tensor, because that's kind of destroying the tensor algebra structure that's that we want to exploit. And what we show in a recent work, the second paper, is that by kind of careful bucketing of the inner products and carefully keeping track of these different inner products, we can get tight sample complexity bounds. For instance, for Gaussian mixtures in some regimes, we only need order k samples for a k component mixture, which is the statistical bound. So in many cases, we can now also address the question of what is the sample complexity of learning this efficiently. Right? And even for ICA models, we have, if we characterize explicitly what is the polynomial that's needed for the sample complexity. So I won't go into these details, but the results are available. Some of them are available online, and the latest one, in fact, what we show is by assuming these components are Gaussian, we get nearly tight signal-to-noise ratio requirements for learning. For instance, just to describe one special case of that result, is if I have the Gaussian mixture and have the variance as sigma in each direction, what we show is for k components, this sigma can go up to root d by root k. Right? So if the number of components k is only constant times the dimension, we are nearly having constant variance in any direction. So and indeed there is degradation as I have more components. So compared to more kind of classical clustering results, which depend on separability, separation between the mean components, here what we are assuming are these incoherent components. But on the other hand, when the number of components is small enough, these tend to be better than the clustering methods. So I would say that they have different regimes of operations. So, unfortunately, I can't go into those details here, but I'll be very happy to chat offline. So, in conclusion, I attempted to give a very broad overview of these tensor methods for various different latent variable models, these topic models, and community detection problems with mixed membership, setting. And in practice, what I showed was that these methods are very easily parallelizable. In fact, we have a cloud-based implementation that my student did at Microsoft Research. We're hoping to open source this very soon and release this. And that we can now run it at essentially any scale of data that we have. And we saw that in the data sets I showed, these are very competitive with respect to these variational approaches. They're much faster and also have good accuracy results. And the software code is available online for any of you who are interested in trying this out for various different settings. Thanks a lot.
Maybe this side first. So, this method, right, the part when you perform the whitening, it seems to be very important.
Yes.
So, if you're under some noise, right, and that prevents you from whitening correctly to the component, how do you address that?
Yeah, so that's a very delicate issue, right? Like the condition number dependence is delicate. And so one way to address this is to kind of assume these if they're incoherent models, then you do the power method without whitening. So at least in those special cases, like whitening is not needed. But in general, this is a delicate issue. Whitening is very sensitive to noise.
Any other questions?